uh, of course, if there is a question on that, please do ask it on our Canvas. I receive all the messages all the time, and I know I'm busy with a lot of classes right now, especially with doing things, preparations, and doing things like that. If I don't respond immediately, maybe somebody else will. At least when you guys post on Canvas, that's one thing. And also, I try to get to it no matter what. So at some point, some of the questions that I think can be postponed will be answered later, or postpone them later. The ones that needs to be answered immediately, I try to answer them immediately. Like, for example, when Aaron asked the other day a question about one of the homework problems, I thought to answer him, but then I decided, you know what, it's better to probably give it to everybody else, and that's why I recorded it on YouTube, and some of you probably were able to see it. Are you guys following the sessions on YouTube, all of you? I know that I don't have the entire class right now, but at least I want to make sure feedback from this session that you guys are, or if you're having difficulty with that.
I think I'm all right. I found the Chapter 8 content. Right now I'm just trying to catch up for most of my classes because a couple of my classes just now figured out how to actually do online.
Okay.
Now I just have to catch up in this class and then...
Okay.
All right.
Yeah. Basically, what I'm doing in here is, I don't know if you guys are following the process with which we're doing this class, is I prepare some of the units. I try to put them short, but the ones that we do them together, they cannot be shortened, basically. Like this class is supposed to go for hours. So the ones, for example, for each chapter, hopefully under 20-minute sessions so that you guys can basically go through the session, do one session at a time, do the problems, do the examples I talk about there. And if it's not clear, you go to the book and then ask me questions, ask anybody else, and hopefully we can get this thing processed as fast as we can. I also posted homework today. I don't know if you guys saw it or not for this chapter. Yeah, go ahead, Gareth.
I'm not seeing anything, no. I only see the 27, homework 11.
Oh. It was not posted? I thought it was. Hold on.
Oh, something literally just appeared right in front of my face.
Okay.
But yeah, we have chapter 28 now.
Okay, very good. Yeah, so homework for chapter 28 is ready. Good morning, Andrew. And so I guess there is homework material. I really want you guys to be doing the work. I know some of you asked to have probably a different load of homework. I think this is the right balance. We don't want to have like fewer problems because we are not meeting in class to hammer some of the examples there and do them there. So I'd like you to work on them. And do not hesitate to ask. Like, for example, Aaron asked me a question the other day about one of the homework problems. I mean, you guys asked even during one of our sessions, and we did a lot of the homework problems together. And also, later on, when Aaron, like I said, asked that question, I was able to answer the whole thing and post it for you guys there. Okay, so I see now a lot of people have joined in. That's good. So do ask questions. You have the chat session going on the left-hand side in here. I don't know where you put it on your screen. You can move it, I guess. So do ask questions or intervene in there and things like that for this thing. So let me go back into chapter 28 unless you guys have any question or something like that. There will be no afternoon session today at 11 o'clock because I think we're going to finish chapter 28. We'll do the examples from chapter 28. And then I don't want to start chapter 29 right now because I don't think it's a good idea to put a lot of material, especially when they're quite like this one. So I want to space it out so that you give you a chance to go and work out on some of the examples. Come Thursday, we will start chapter 29, and we should be ready for the exam next week. Actually, the exam was supposed to be this Thursday, but because of the disruption, things have to be moved a little. So the exam is going to be the next week, and it's going to be take-home exam, basically. And I'll decide later on exactly how many problems. Most likely it's going to be 4 problems. And you will have a limited time. It's not going to be like 1 week. It's going to be actually a lot shorter than that to basically figure out the problems. And after the exam, after you turn in your exam, I'm going to have a session of one-on-one, basically, with each and every one of you, basically to ask you a couple of questions to make sure that you're confident in your answers, okay, about those problems. Make sure, basically, that you know what you wrote in there, okay? Does this sound like it's a good plan?
Sounds good.
Okay.
When can we expect the grades for exam 3?
Oh, exam 3, I did not honestly finish grading it because of this disruption and things like that.
Yeah.
Yeah, okay. It should be posted before exam 4, okay? So that you have an idea of how, I mean, hopefully this weekend you will have it just before exam 4 so that you know exactly where you stand in terms of all of your grades, okay? Including the other materials, not including the last two homework, but the homework that you're posting right now, which is due the Thursday, and there is another homework due next week. So those things will not be posted before the exam, so they will be posted after the exam. So those are the materials that will be lingering out. That's one thing. The other thing also, next Tuesday, there will be a lab. So we will have our lab because I think we will be ready for, we would have done the inductance by then. So we should be ready for this lab. I mean, the concepts should be ready. Okay?
And how do labs work on here again? Are we going to meet on Zoom and then go to the website, or how's that going to work?
Okay, most of the labs are going to be simulated. So basically for this lab, is going to have, you're going to have an RC circuit simulation, an LC circuit simulation, and an RL circuit simulation. And basically, you're going to change the values of the resistance, you're going to change the values of the capacitance, and you're going to change the values of the inductor in each of these configurations. And you're going to find the time characteristic for each one of those things. And of course, you're going to compare the theory with what you're getting from the simulated answers. So in other words, I know this is one of the things that I hate the most about this online thing, is the fact that you guys are not doing really hands-on the way it's supposed to be, so we're doing virtual. But that's, I guess, in my opinion, it's a small price to pay for right now because of this pandemic that is really sweeping the entire world, not just the country. And we want, safety is more important at this point than anything else. So hopefully this will alleviate a little bit. And since I'm scheduled to be your physics 3 instructor also next semester, so hopefully this will be fixed, and maybe we'll do some catch up in terms of hands-on with these things, because I'd like you to have as much as possible of a feel of what an inductor look like and what a capacitor look like, because if you're going to go and break some electronics and try to work with it, that's something that you need to be familiar with. That's one thing. The other thing also, it's still not completely out of the realm of possibility that I will have projects in this class, hands-on projects, where you do them on your own there. And hopefully I will show you where to go and get cheap enough material so that you can start working with them and submit that as part of your work also for this class. Okay?
I would like that. I've always kind of wanted to do like those home done projects because I thought they were kind of interesting.
Okay, okay. I already have a project for the motors that's going to happen. That's something that I did in the past in class, and it was a lot of fun. And people basically, they were very excited about making the motor run as much as possible with magnets, which are accessible even from this magnet in here that I have with me. This is a bar magnet. Actually, it's a bunch of bar magnets. And I have other magnets also. Unfortunately, I cannot share my magnets with you guys, but you should have access to those. And also, if you go to Home Depot, you could go and get some small, basically, copper wires that are used for, they use them for basically for home, what is it? Homework, for people working in their homes on their electrical things and things like that. So there is an aisle there on Home Depot. You can go and grab a couple of wires from the higher gauges, basically the fine wires. And you make them into a, you can roll them against something like this once it's rolled, and then you come to the end. Usually they're protected, so you need to shave the ends of them and then use paper clips like this one in here, and you can form them into, let me show you. Basically, you open the paper clip like this one, and you run the shape part in here, and you will have another paper clip in here, and now you have what looks like a loop, basically, going around and around. I actually can build one for you guys, and you put it next to a bar magnet, you connect it to the battery in the other end, and now you have a motor running. So, of course, it's a lot of fun, basically, so that we don't lose the fact that this is still a physics class, not a math class, because it looks like we're doing a lot of things in theory, and we're talking in terms of concepts of how things should look like. And even though we simulate the circuit, it's still a simulation. It's not a real thing. And we need to have a feel for it. Now, having said that, does not really discredit simulation. In the old days, before the advent of simulation, people used to do the theory, basically the calculation, which can only take you this much. It doesn't really take you a lot. So you really have to go and do the actual model. So what you do in that case, you go and invest in equipment and build the model and see whether or not the results you get off of it work or not. But before now, since we have simulation, that's actually a necessary step now. It's not just some sort of an unnecessary thing to do. So you do the model, the theoretical model, basically the math that we do in class together. Then you go into a computer with C++ or whatever other programming language that you like. You build the model, basically in a numerical model, and you see how that works. And if it breaks, nothing, basically no damage, it's not as costly as really going into buying an investment and making a model. So then once that works in a numerical simulation, besides you can go to a lot of extremes in a numerical model. So modeling is still not really, or simulated environment is something that is useful in a sense to learn and do, because then you can break things without having to break a lot of things actually, and it's a lot cheaper. Now, when you go actually and build your model, which is still a necessary step also, you know exactly where to go and what to do. So then you learn from your simulations what happened, and then you go and build the model of what the final design is going to be, basically. And then at the end, you go and you build the thing. So there was a layer that was added now in the process, and that layer now is going to be our emphasis in terms of how we learn physics. So as engineers, you guys are going to be working now in a lot of steps, and some of you will be working only in one step. If you're going to be an engineer, for example, in an environment where you do a lot of simulations, that's probably your livelihood. So that's not completely a lost cause, basically, the fact that we're not doing what we also should be doing, namely in a laboratory. Okay, that's still an important thing, in my opinion, that we need to do. Okay, so I see that we have most of everybody in here. I'm still missing few people actually. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We still have missing 3 people. Okay. Okay. For those who came in a little late, of course, there was a lot of material that is posted on YouTube, and I really want you guys to make sure that you have access to that channel, because, as I said before, it's kind of hard right now when you upload a lot of videos, basically, and then every time you upload a video, you're going to go and have people and tell them, okay, here is a link for a video, here is a link for a video. That's a little bit tiring, and it starts to accumulate on your inbox, especially with other instructors and other things, and you probably will lose it in the mix. So what I'm suggesting guys you do is go to there's a link in here for all of the videos that I upload. I posted on the chat session. Go and subscribe to it so that you will be notified by Google or something like that. Hey, there is a new video. Now, if it's not your class, just ignore that notification from Google. But you will have it firsthand, basically. The minute it's uploaded and ready, you'll have access to it. You don't have to wait for me and basically tell you guys that it has been uploaded or not. And if it's not your class, then ignore it. If it's something of your class, then you must probably do that. Go through the video and look at it and see how this thing works. Okay, so chapter 28, there was a lot of parts that were in there. I'm going to go quickly on what was uploaded to make sure to answer any of the questions that you guys have right now, and then we move on. Yes?
Sounds good.
Okay, so I'm going to share the screen again, my screen, with you guys. And how can I move this thing? Man, it's become so big. Okay, I'm going to put it in here, that's fine. So basically, this is chapter 28. We started it actually together, I think, no? I don't know if we started together or we started it on, I think we did start together. Anyway, chapter 28, basically the biggest question is, where is magnetism is coming from? Okay, and the answer in a nutshell is coming from the current, coming from the basically a charge moving in a circuit. And I know I started with this expression for a charge moving by itself and basically calculating the magnetic field for it, but I said later on that, hold on, that's not really a good starting point. I know the book starts with it, and I try to basically give you that. And the reason why it's so is because it gives you, if you wish, a justification for what comes later, namely the fact that experiment has shown that a current running through a wire creates a magnetic field. And the magnetic field, the strength of this is inversely proportional to the distance from the element of the wire, and a distance squared, that is, inversely proportional to the distance squared, just like Coulomb's law, just like the law of gravity of Newton. There's a lot of laws, apparently they have this behavior, which is 1 over r squared. And it's also proportional to the intensity of the current. The stronger the current, the stronger the magnetic field. It's interesting to know, of course, and that if there is no electric field, there is no magnetism. So basically that answers the question. If I is 0 here, there is no magnetic field, no magnetism. So what causes magnetism is a current. And I asked toward the end of this chapter, we're going to try to understand what a bar magnet is, because we just said that, hey, currents create magnetic field. So what's happening with a bar magnet, basically like this magnet, the one I was showing you earlier. So what's going on in here? Why is this one attracting this piece, for example, and when I reverse it, the polarity is actually repelled. So that's really something that we need to understand. So there must be currents in here, and we have to explain that. So that's one thing. And the other thing, of course, it has to do with the medium where we conduct this experiment. If we do it in the medium other than vacuum or air, the constant mu changes. That constant is called the permeability, and is a property of the medium where we conduct these things in here. Okay. And then it's given by that right-hand rule. We have to find the unit vector, and then first of all the element where the current is running through. Then you have to find the unit vector, and then that's in the direction of the magnetic field is. So the direction of the magnetic field is given by the right-hand rule, basically. And the right-hand rule is everywhere in this, from chapter, I mean the entire course probably. You need to have a little bit of vector calculus in order to understand it to begin with, but you have to also have a full grasp what vectors are. I know you did that in Physics 1, and Physics 1 basically you learned about the torque and the angular momentum. The angular momentum was basically, if you guys remember, it's R cross P, and the torque was R cross F. So there was a cross product then and there in Physics 1, but this one has it everywhere. I mean, especially when you talk about magnetism without the right-hand rule, you cannot understand it. And if you're not paying too close attention to this, it's going to be confusing. Okay, so it's really, really, really important that you understand what's going on. Here, this is the Butin-Savart law, and basically this is, again, you can think of it as based on experience, based on observation. So what's going on in here is that you have the magnetic field, the element of the magnetic field that is created by an element of a wire, dl. So dl in here stands for a small portion of the wire. dl stands for the length of that wire. It's a vector, just like any other vector, and it points in the direction of the current. Because a wire by itself, like this wire in here, a wire by itself has no direction. But now how do I know which way it's pointing? It's pointing always that the current is flowing down this way, so this is the direction of dl. Now, r hat, again, here is a wire. Let's assume this one has current in it. And I want to find the magnetic field at some point in space. So this is where r is, the distance r between where the current is running and where I want to find the magnetic field. R hat is that unit vector that points from the wire that has the current in it all the way to the point where we want to find it. So this is not a good expression. If you compare it with Coulomb's law, of course, Coulomb's law is a lot easier. And even then, you guys remember that we had to do Gauss's theorem, and then we had to do a lot of work in there, and we defined the electric potential, and we did a lot of work with that more simplistic, basically, formula that was only E is proportional to R hat. In the case of electric field, you have a charge, and a charge produces electric field that points away from the charge. It's like basically in everywhere in space. The only problem with it is that the field is coming and going everywhere in space. So whichever way you look, it's like a hedgehog, basically, where you see the field lines are pointing everywhere in space, and they're following R hat. So if you have the source here, and you have a point in space in here, this is R hat. If you want to find it in here, this is R hat. So R hat is again pointing in everywhere in space. And that is the direction of the electric field. If the charge is positive, then the field actually is leaving. If the charge is negative, the field is going in. So that was basically what we discovered with the electric field. This guy now is different. If this is R hat, the magnetic field is perpendicular to that because of the right hand, because of the cross product in here. dB is perpendicular to R hat and perpendicular to DL also. So that's why you have the right hand rule in here. And you cannot have magnetism on a two-dimensional surface. You cannot draw it really on a two-dimensional surface because it has to be 3D. I mean, it has to be in 3 dimensions. It cannot be drawn because of this cross product. And cross product, you have plane formed by 2 vectors. You need the third plane in here, the third direction in here, which gives you the direction of B. So that's basically it. In other words, if DL and the R hat make a plane, you need the direction perpendicular to them to find where the magnetic field is. And the magnetic field, again, is given by the right-hand rule in here. So, again, we calculated this. We took even an example in here. We took a wire that has a current running over it. It's a huge current, 125 amps. It's not a small current. And we found the magnetic field. At some points, we used even this. You guys have seen this form in here in Physics 1, didn't you, for the cross product? I need some feedback. Yeah, somebody chatted. Hold on. Yes, okay, good. So that's really, I mean, if you have seen it, it's going to be very, very useful because without it, we cannot do much in here, okay? In the example that Aaron asked basically the other day, is he in here or not? Is he with us today or not? I don't see him. Okay. Anyway, I know some of you probably were tempted and to use the right, you could do that. You could use the right hand rule and answer problem, what is it? Problem 51 from the homework. But all I did was basically follow this definition of the cross product. Basically, it's not a definition. It's basically the same as the other one, basically. It's an equivalent form of the cross product. I know we defined it as R, I mean, one vector times another vector, and magnitude of one vector times the magnitude of the second vector times the sign of the angle between them, and the direction is given by the right-hand rule. That is exactly equivalent to this one. Some useful information in here that we did last time, and it's very good actually that since we're going through this quick review here, is that this expression has in it this identity. I hat crossed with J hat gives you K hat. That's a useful identity. And from it, we are going to get all of the other cycles, basically, when you do a cyclic rotation of this expression, when you move everything one step to the other. So you move the K to the J, you move the J to the K to the I, you move the I to the J, and you move the J back into the K. It's still the same thing. In other words, K hat crossed with I hat gives you J hat. So that's one of the properties of the cross product, actually. In other words, that's the rule that we're talking about in here. If this is I hat, J hat, and K hat, if I start with this one I hat, this becomes J hat, and this one becomes K hat. So those are some of the basic properties of the cross product. Now, if I switch them around, if I do I hat cross with J hat, it's not the same as J hat cross with I hat. to the negative value of it. In other words, it's not commutative. You cannot switch the order of the operation matters in here. Okay, so these are some of the basic properties that hopefully you had a little bit of discussion with it in physics 1, and that becomes useful when you're doing the homework problems and you're doing exam problems. So this is very, very important information that you need to remember. One of the things also that you need to remember is the fact that if I plot any vector with itself or with any vector parallel to it, it's going to be 0 because of sine of 0 is 0, sine 180 degrees is 0. So that's an important useful thing in here too. So if you ever want to find if two vectors are parallel to one another or anti-parallel to one another, they're in the same direction, just do their cross product. If the cross product is 0, that means they're perpendicular. If you want to find out if they are perpendicular to one another or not, do their dot product. If the dot product is 0, these two vectors are actually perpendicular to one another. So those are some of the usefulness of this too. The dot product is a cross product is actually called it's an internal operation. In other words, a vector cross with another vector is a vector. It's an operation that happens in the space of vectors within them. The dot product actually is not an internal operation, it's an external operation. You take a vector, you dot it with another vector. You don't end up with a vector when you dot vectors. You end up with a scalar, which is completely different beast. So some of this vector stuff is useful for us. Okay, and later on, there's 2 more theorems that we will need from vector calculus, and we'll hopefully discuss them, namely Green's theorem and Stokes' theorem. Did you do this too in math? Let me tell you what they are. Okay, Green's and Stokes theorems. Have you seen this in your math classes? I don't know which calculus you did. It's supposed to be probably class 3 or something. Anyone? Gino also is not here. Yeah. Yeah, somebody is saying toward the end, Jackson is saying toward the end of class 3. Okay, so we will need them basically. If we have time, we'll prove them actually. It's kind of funny, basically, when we talk about Green's theorem, it's not hard to. Actually, it's a little bit more difficult, honestly. Stokes' theorems, both of them have the same level of difficulty. As a useful resource, and I know I put it in my syllabus for this discussion in terms of trying to understand the physics behind it, and that's the approach we're going to take, because we need this part in here later on when we're doing, I think, chapter 32, which is coming not too late from now. Is use Feynman lectures. Feynman lectures has this, and Feynman lectures are free actually. You can find the entire books online from Caltech, and I think I have the link for you guys on my syllabus. And he makes a very good discussion about them, and probably we're going to follow a similar approach in here when we introduce them, trying to use them in order to move on with this course. Okay. So let's continue with our review for this chapter, for what we did so far in this chapter, I guess. Okay, sometimes my screen in here freezes, and I think probably it says to do the chat, no? No. Okay, that's not good. So I'm going to close this screen and come back to it, and hopefully it's unfrozen. Okay. Okay, so let's share that screen again. So again, so we did that example, we discussed the magnetic field, we went even through the example calculations, and then we did something very important from last time, basically. We took a wire of finite length, okay, I called it 2A. And then we found the magnetic field produced by that wire in the middle, on an axis passing through the middle. So we didn't find it in the middle, actually, we found it somewhere along that axis, okay? And the expression has to do with the 1 over distance, which is important in here at the end. So the magnetic field turns out to be something that has 1 over y in it, okay? And that's important because if we put it really when y is equal to 0, we're going to have a problem here. The magnetic field will be too big. So, and the magnetic field is in the direction of k, and now it's given by that right-hand rule, and it's easier to actually do it with the with this basically version of the right rule. Right rule, I guess. So basically what you have in here, you have a current flowing in one direction according to the thumb, and then the magnetic field basically curves around it. Okay. So this is basically what we calculated. Then we took the limit when the wire is infinite. When the wire is infinite, basically y is very, very small compared to A. In other words, the wire is so long and we're trying to find the magnetic field very close from it. I said then and there that this is an important result, and hopefully you guys would remember that. Is Julian with us? Because Julian last time was not able to log in, and he ended up going to John's place. I just want to make sure that he's... John, is Julian there or not?
No, he's not here.
Okay. Yeah, okay. So basically, so this is an important result, like I said, and this one we will need it for our actually we'll need it today, okay? So again, we came on after, which is actually, I recorded this session for you guys, I think on YouTube, and I took 2 wires now and tried to understand. Since one wire can produce a magnetic field, and another wire can be affected by that magnetic field. Now there is a possibility if I have 2 wires, basically, with a current running through them, then the 2 wires can interact, okay? And that is something that is important in here. Now, if the currents are running in the same direction, well, experience has shown that these 2 wires will attract one another. If the wires are, the same direction, they actually repel, like all okay. And then when one of the currents is going in one direction and the current is going in the opposite direction, in this case, it's the wires attract, okay? So that's basically what this thing needs to, we needed to show that, okay? So, again, we calculate the magnetic field created by one wire in the place where the second wire exists, using the formula from above, that's all, the one that we found previously. So using this formula, I can find the magnetic field that was created by this wire where the second wire exists. And now we use the results from chapter 27 to find the force exerted on that wire by this magnetic field. Now we have the force. But of course, the force has to do with the finite length of the wire. That's why we had to introduce this L. Usually the wires are so long, we don't care about, and they're too close from one another, we don't care about the distance. Once we have that, then we have the force, and we define the quantity in here, which is the force per unit length. Namely, we get rid of L again. So we introduced it just to find the force because we need that for this formula in here from chapter 27. And we get rid of it again. All we have to do is just basically divide by that length. And now we have a Newton per meter. In other words, somebody asked a question here. Hold on. Okay, yeah. So basically what we do in this case is here is the trouble, okay? Let's say, for example, I have a wire, very long wire, okay? And another wire, and I put the 2 wires next to one another. And for some reason, they start to repel or attract, but I want them to be in their places. I can basically hire a bunch of people and tell them, you know what? Because these things are trying to move to one another or move away from one another. Can you guys hold them in place? So let's say, for example, 10 people, they come in, and each one of them hold the wire in place so that it doesn't move either up or down, depending on the direction of the current. And of course, if I bring a longer wire, I need more and more people. Basically, 10 people are not going to be enough. So basically, the concept of the force per unit length is, this is basically the idea behind it. The longer the wire, the more stress it's going to undergo because of these forces. That's why we define this force in here. So this force in here is force per unit length, not to be confused with something else. So this is force per unit length. And the unit for it is Newton per meter because the length is still in meter. So that's basically what we have found. And again, the first wire can impact the second wire. I don't know what's calling in here. The first wire can impact the second wire. I see. Hold on. I think one of you guys is contacting me. And so probably he or maybe somebody is having difficulty connecting quickly in here. Let me check quickly Canvas to see if somebody was contacting me in here from your class. No, not through Canvas at least. Okay, somebody from Canvas, at least from Itata, is trying to contact me. Sorry, I cannot get to them at this point. I was trying to see if I can help them quickly, but apparently we can't. Anyway, they are going to access this recording later on. Anyway, here is the deal. So one wire exerts a force on the other one, and we found it. And I said in the recording, if you guys were able to look at it, is there's two ways of calculating the force from now the second wire on the first one. First of all, there is a one without doing anything. You can find it, and namely the fact that you go back to physics 1, and that is we have two objects interacting, and if they do interact, and one of them exerts a force on the second exerts a force on the first, with a force that is equal in magnitude and opposite in direction. So once we found F21, in order to find F12, all I have to do is just use the same value and change the orientation of it using the third law of Newton. Or go through the trouble again of finding the magnetic field created by the second wire in this point where the first wire is. Once you find that magnetic field, now use the chapter again from chapter 27, find the force that is this wire 1 now is going to be subject to because it's in the presence of the magnetic field due to wire 2. And from here, you're going to find that force. It turns out to be the same value in magnitude and opposite direction, exactly how physics 1 has predicted these two forces to be. So either way, it should give the same answer. Remember, you guys, I always ask, does it make sense? Does everything fit together? This is one way of doing it. I mean, there are two ways of getting to the same answer. And since there are two ways of getting the same answer, the answer should not change. The answer should be the same. Whether you get it this way or that way, the answer has to be absolutely the same thing. So that's basically one thing that we did in there. So that was another point. Another point in here that is very useful, if you have a wire now that is in the form of a loop. So this is like a circular loop. And if you have a current running through it, again, we use Bjorken-Savart's law, and then we will find the magnetic field. The magnetic field will point in the positive direction if the current is going counterclockwise. Basically, if the current is going counterclockwise per the right-hand rule. I know probably on the screen, at least, I don't know how it looks like to you. Looks like I'm using my left hand because I think the reflection, again, this is Snell's law that we did in the previous chapters. This probably looks to you like it's the right hand. At least that's how it looks to me in here on the screen. Again, this is probably a visual problem that's all because of the reflection on the screen. But again, this is the right-hand rule. So the current now is going per counterclockwise. And if that's the case, the magnetic field will point upwards, or basically Bjorken-Savart's law. All of these things are connected because before, for example, what we had actually the other way around. We had a wire that has a current going this way, and that wire, the magnetic field curves around it. Now the situation is different. We have a current curling, and the magnetic field is pointing upward. Do you guys see the difference between the two? The two have swapped places basically. Now, in the first situation, what we had the current going up and down in a wire, in a straight wire like this one, So we have the current going up and down. So if the current is going this way upwards to the ceiling, then the magnetic field in every point in space is going to curl to the right-hand rule. Now we have a situation completely different. Actually, the current is actually the one that is curling in a loop, and it's curling clockwise. So the current is going this way. The magnetic field is the one that is pointing upwards. And that's basically the result that we found. And the magnetic field due to a loop in here. The integration is going to be very, very straightforward for this problem. It's a lot easier than, for example, an infinite wire or even a finite wire. Because in this case, everything is constant in here. The angle theta doesn't change as long as you go through the entire loop in here. It's the same angle. And the r does not change of the loop. The distance from the loop to the point where you're calculating the magnetic field doesn't change. Everything is the same. The vector, the length of r itself doesn't change. It's always square root of z squared plus r squared, because as you loop around this wire, which is in a circular shape actually, the reason why it looks elliptical in here, because we're looking at an angle. If we look at it straight up, it's going to be a circle, but when you tilt it, it looks like it's an ellipse. Now, if you do that, that's basically how the integration, all you have to do is integrate dl from 0 to basically the entire length of the circumference of the circle, which reduces big R. So the integral at the end of the day will be just 2 pi r, which cancels the 4 pi. The 2 pi cancels the 4 pi, will be left with the 2 in the denominator. And everything is straightforward in here. The cosine theta in this case, because you needed to project this vector dB in this direction of the z-axis, the other two axes, they cancel the components, because this one is positive, the other one is negative, and they are the exact same magnitude. They cancel everywhere. So the only component that survives this whole thing is the components in the z direction. And that clearly involves cosine of this angle theta. And this angle theta is exactly this angle theta, because both of them are components the same angle in here. So at the end of the day, cosine theta is just the adjacent, which is r divided by the hypotenuse, which is the little r in this case. So everything else would work out to give you this expression for the magnetic field at any point on the loop. I mean, on an axis that runs through the center of the loop. So that's basically the result for the loop, and this is where we are right now in this chapter. Any questions so far of where we are? No? Okay. So right now we're gonna go through a very important theorem called Ampere's theorem, because that's going to be much useful for us in terms of doing calculations and doing all of these integrals in here. An Ampere's theorem basically is equivalent to Gauss's law. Okay, is equivalent to Gauss's law. Somebody sent me a message right now. Okay. So this theorem is so this is for magnetism. This is for magnetism, and this one is for the electric field. This, let me just remind you exactly what Gauss's law looks like. Gauss's law basically says that the integral of the magnetic of the electric field dA, we call this one the flux, when you integrate it over a closed surface, is equal to the charge enclosed divided by epsilon naught. So that's basically the result we found from Gauss's law. So basically, the flux of the electric field over a closed surface, so the surface has to be closed in here in order to use this Gauss's law, is equal to the charge enclosed by that surface inside the volume where the charge, where you're doing the calculation, divided by the properties of the medium, in this case, the permittivity of the medium. So basically, you have to have one thing in here, which is very important. Okay, let me get the pen. So you have to have a surface in here enclosing some. So this surface is a surface which is closed, okay? I'm trying to show you that it can be any shape you like, okay? It doesn't have to be a sphere. So this surface now is enclosing a bunch of charges inside, And if you count how many charges there are, taking into account the fact that some of them are positive and some of them are negative, there is some cancellation in there, algebraic cancellations in there with some. And at the end of the day, the net value can be either a positive value if, and the field will be coming out of that region. Of course, it will be deformed a little bit because there is not necessarily a uniform distribution here. So the field lines may have some weird structure, but the net number of them, how many of them will come per unit area, that is what the flux is. That is the flow, the rate at which they are coming out of that region is given by that expression. So that's basically how we define it last time. Now, if the net number is negative, then this picture will be reversed. So if this number is actually negative, so this is, if the charges were negative, so this is how the field lines will be coming in. So in other words, this number will be negative on the other side. And if it's negative, that means there is an influx of field lines coming in, okay? Because the dot product in here of EDA will be a negative product because the surface is coming out. So this is dA, and the field itself is going in, E. So EDA will be a negative number, and if EDA is a negative number, that means the field lines are going. Always the surface is coming out, okay? In the first case, when the net charges were positive, E and dA were parallel, therefore that number was positive. Now, in the situation where the positive charges and the negative charges cancel each other everywhere, there would be no influx or outflux of field lines, and the net flux is there. So this is something we saw way back when we were doing the electric field. Now I'm going to define another quantity called the circulation of a vector. So what I have in here, I have a vector. I'm going to start out and say that this is going to be the vector B, because the vector E that we did has no circulation. The vector E does not circulate. It's always going to leave a point. And if you try to find it, let's say, for example, let's take a point charge in here just to see what I'm talking about. So this is a point charge. And if I'm trying to find how much is going to go around the point charge in here, I'm going to go into this direction and try to find the dot product of this vector E with the direction which I'm going to circulate in, which is dr. The dot product is going to be, in this case, 0, because the angle they make between one another is 90 degrees. So the electric field does not circulate. If I'm interested to find how much the vector field goes around the charge, I'm not going to find any value. I'm going to find 0. So the electric field does not circulate. However, the magnetic field does, because we just saw that a current running through a wire will create a magnetic field that goes around it. Okay? So if I'm interested in trying to find that, so this is basically what's going on in here. So first of all, the circulation of a vector along any path in here, which is going to be a closed path again. So this is a path integral. This is not an integral over an area. Is B dotted with dr. Okay, let me write a dl in this case because I don't want to confuse it with the radial direction in here. Is equal to, this is the circulation of the magnetic field in general. This is the circulation over a closed path. So do you guys see there is some difference between the two here up front? The flux is a integral. The circulation is a single integral. Okay, that's one thing that you're going to find in here. If we do Ampere's law, the result we're going to find, and we're going to prove it, is equal to mu naught times I enclosed. So this is Ampere's law. I just put the statement in here. So let me put the statement for Ampere's law, and we're going to prove it later on. Any questions so far? I know some of these concepts are kind of strange to you guys. You have never seen them, especially in math, and they may kind of coming from everywhere to you guys. I'm trying to give you a description of what they are, and then we'll talk about them a little bit more in detail. No? So let me give you this statement for Ampere's law. So Ampere's law, which is the equivalent to Gauss's law, states the following. The circulation for the magnetic field over a closed path is equal to the product of the permeability of the medium. That's an important thing. Remember, when we were doing the Gauss's law, we said dividing by permittivity in here, we're multiplying. Everywhere we saw dividing by epsilon naught, we're now multiplying by mu naught. Permeability. I don't know the space in there, that's why I wrote it in here. Permeability of the medium. And the net sum of the currents so the currents now will have a sign in them too. Some of the currents will be coming into the surface, some of them will be coming out of the surface. And if I'm circulating counterclockwise, anything going into the, basically following the right-hand rule, is going to be positive. Anything opposite to it is going to be negative, okay? So we have to have some signs in here. So the sum is going to be a net sum, so that's going to be an algebraic sum, just like we did the charges. Except the charges, they come positive and negative. It's very easy to find. This one, you have to see which way you're circulating in order to find the positive and the negative. So the sum of the currents going into or out of the surface enclosed by discharges, by this path, enclosed by the path. It's a big statement in here. You guys can hear me, because I think I'm hearing something in my speakers in here and they have not been working well for me. Yes?
I can hear you.
Okay, very good. So, okay, very good. Okay, so basically, how the circulation then works. The circulation is just the dot product, just like the other one, for the flux. Except now we have to find the path where we're circulating, where we're going around. Basically, if you the whole thing is coming from the analogy with the fluid dynamics. Basically, in fluid dynamics, liquids flow. That's where the flux is coming from. But if they find an obstacle, they go around it, basically, and they start to do some circulation sometimes, okay? And if you have water flowing and you open a faucet underneath, it's going to spiral into that faucet in there. So fluids, they do both, except in here, the electric field does not circulate. At least electrostatic field does not. We'll see later on another beast of electrostatics, electric field that does that, but not electrostatics. Electricity never circulates. Always going to flow in or out, depending on the sign of the charges. The magnetic field, on the other hand, circulates around currents, basically, and circulates positive counterclockwise and negative clockwise. So that's something that we have to be aware of. Now, the magnetic field does not flow. That's another thing, okay? The reason why is because, again, there are no monopoles or north poles or south poles by themselves. So for the magnetic field to flow out of an area, it must go from here and leave somewhere and never come back. And that is not possible, because then you have somehow a monopole. So one of them does the other one doesn't. So one of them flows all the time and never circulates, the electrostatic field, and one of them always circulates and never flows, and namely that is the magnetostatic field. So both of them don't do that. Okay, in the case when time is involved, these two things start to get mixed up and the thing becomes a little bit more complicated. Okay, So this is Ampere's law. Let me try to prove it at least in terms of a wire, and see that once we have it for a wire, it's going to be the generalization for everything. So I have a wire in here, and I go to a point. This is an infinite wire, and I go to a point around it in here. And if I look at the magnetic field in here, it's going to go around, circulating it in here. And we found it. It's going to come out of this area and goes into here. Okay, so that's basically how the magnetic field is. For a current running in this direction, I. So if I come in here and look at this current from one side, basically from where the current is coming, this is how, to me, if I'm looking at the wire from this one, of course, this is an infinite wire, so I have to go very, very far to the other end and look at it. So this is how the wire looks like to me. So the current is coming in here to me. So this is that view. And what I see in here is that the magnetic field is going in a circle, basically around it, at a distance, which I'm going to call R, okay, at a distance which is R in this case. So the magnetic field is given by the expression that we calculated previously is equal to B, and it's going to be in the angular direction, in the azimuthal direction, not in the radial direction. Unlike the magnetic field, unlike the electric field, which is pointing in the radial direction, this one points in the angular direction, if you wish. So B is in this direction. So if this is the radial direction R hat, and this is the direction theta hat, then B is actually in the theta direction and is given, not that it depends on theta, but at least it's in the theta direction, which is perpendicular to the radial direction, and its value we found it to be mu naught times the current I divided by 2 pi times the distance, and the distance is R, times in the theta hat direction. Everywhere theta changes, the radial direction, I mean the azimuthal direction changes, this thing changes with it, so it's going in a circle, basically, okay? So having said that, then, this is a vector now, since I gave it the direction, a vector now. So having said that, if I take this direction now, dl, so dl is along this path also. So dl itself, as a vector, is going to be dl, the length of the arc, basically, the arc length, and the theta hat direction. So from here, I can clearly see that d times dl is simply equal to mu naught I over 2 pi r times dl. Sine of the angle, I mean theta hat times theta hat is 1, because theta hat is unit vector in the azimuthal direction, and its length is 1, and it makes a 0-degree angle between itself. So the dot product basically boils down to this expression. If I'm interested to finding the circulation, it doesn't have to be along the circle, by the way. I can calculate the circulation around any path in here. It doesn't have to be a circular direction. It can be any path you like, okay? So in other words, some R's are bigger than R's. This R is clearly smaller than this R, okay? So R now is a variable that changes. So the magnetic field will be stronger in here than in there. The magnetic field will be stronger in this point in here than in here. But the value then, I'm interested trying to find the arc distance. And if you guys remember from physics 1, it's not hard to see that if I have a displacement along the arc by an amount d theta, this arc displacement is equal to r d theta. You guys remember this expression from physics 1? When you have a vector and you move along the azimuthal direction only, then this is the arc distance. For a whole circle, it's 2 pi times r, but for a small distance d theta, it's not the full circle, it's 2 pi, but rather a fraction of it, which is d theta. You remember this expression from your physics 1 class? Yes or no? The arc displacement, when you did the circular motion. Okay. Since somebody answered that they don't remember that, let me give you a quick, brief, basically, introduction of this idea here. Okay. From physics 1, basically, what you have in here, you have this is the center of rotation. This is the vector r. This is the vector position whose coordinates are x in the x direction, y in the y direction in 2D. and z in the z direction when you start 3D. You're familiar with this concept? Yes? I need some feedback. Yes, very good. So, now, if a particle is going to do a motion in general, not necessarily a circular motion, it's going to either increase its r from r to r plus dr. So basically the radial direction increases from r to r plus dr. So increment the radius by an amount dr. So it was moving this far from the center of rotation, now it's moving this far, or moving closer. So dr can be positive or negative. So that's one way of doing it. So it can go through the radial direction up and down. Also, it can go through the direction of the angle. That's another way of for its motion. Actually, that's the radial, that's the circular motion. So the circular motion could retain its r itself. It does not change it, but goes through an arc by an amount of d theta. And the arc distance in here is given by r d theta. And again, the radius is r, and the displacement is d theta. And if you guys remember from the which class is that? Basically, you know that the circumference of the circle is 2 pi times r, correct? And 2 pi is the angle going once around the circle. Yes. Okay. So then, for a small displacement d theta, this is how much it's going to be. Now, for a general motion, it's going to be the sum of the two. In general, a particle can do both. So it can move a dr amount in the radial direction and can move also an r d theta in the theta hat direction. So this is the theta hat direction and this is the radial direction. It can move radially or in the angular direction. So basically, this is how you can think of it too in terms of the algebra. I really probably I should put some notes. Maybe I will add some. I will pen some stuff in here. A little bit of a review of physics 1 for you guys. Okay, so this is a vector r, which is how it's expressed. Now, when you do the derivation dr, the differential form for this vector, basically what you're saying in here, the vector can change both in the radial direction by an amount of dr in the radial direction, but also the unit vector itself r, which can change, so it's going to be r, and this one is going to be actually in this case in the theta direction now. So the vector when it changes in the other direction by an amount of d theta. So that's basically how the displacement is. So what I'm going to do, I'm going to include a little bit of a review for you guys to connect it with physics 1. But the point being in here is this is dl now. So the dl, since we are moving in all the directions basically, as far as the path that I chose, which is a general path, not necessarily a circular path. So dl itself is what I'm talking about in here, which is this vector. It doesn't matter this component in the r hat direction because the vector b is actually in the theta hat direction. So b times dl b times dl, and dl now is this general displacement on that path. The r hat times theta hat is going to be 0 from the expression here. Remember, b is always only in the radial, in the azimuthal direction, it's going only along the theta hat direction, and dl has two components. R hat dotted with theta hat is going to give me 0 because they make a 90-degree angle between them. And theta hat dotted with theta hat is going to give me 1. And r from here will cancel this r from the denominator in terms of the expression for r for b theta. And at the end of the day, when I do this product, it doesn't matter what r is, it doesn't matter which path I take. The bottom line is this product will end up to being equal to mu naught I over 2 pi. The r cancels from the numerator and denominator, and I will be left with d theta times theta hat and divided by nothing. Basically, the r from this expression for the magnetic field and the r from r d theta in here will cancel, and this is what I will be left with. So now I'm going to find the circulation of this vector along any path, as long as it's closed, of BDL. And this is going to be basically the integral from mu naught I, the current in this wire, and I took only a single wire, the integral over a closed path of d theta. There are two possibilities in here. Either the wire is actually enclosed by this path, like this situation, in which case, when I start from an angle, I go 360 degrees and come back to it. And d theta, when integrated over a full cycle, is going to be 2 pi. And the 2 pi will be exactly what is needed to cancel the 2 pi from the denominator. So this integral will be 2 pi. And the 2 pi cancels that 2 pi, and it's mu naught I. If now the path does not include any charges, this is the situation we're in. I have a wire in here that has a current coming from it, but I choose this path. So I start from some point in here. Let's say, for example, I start from the bottom. I start from this point in here. I start from theta 1, go through the whole cycle, and come back to theta 1. So the integral is going to be from the initial angle, go to another angle that is not theta 1, so let's say theta 2, and come back to from theta 2 back to theta 1. And at the end, the two angles, the two sums will cancel. So whatever contribution, positive contribution, let's say 45 degrees to 90 degrees, for example, I added 45 degrees, but when I go from 90 back to 45, I cancel that increment, and it's going to be a zero integral. So this expression is equal only to 2 pi once I go full cycle over a wire that is contained through this integration. Otherwise, this value is 0. So that is for a single wire. Now, if I have more than one wire, and if they're going everywhere, so if I have a bunch of wires, some of them are coming out of the surface in here. So this is carrying current I1, this is carrying current I2, this is carrying current I3, and they're all coming out of the surface. And if I have in the same time this wire carrying a current I4, this wire carrying current I5, and if I'm trying to find the overall magnetic, the circulation of the magnetic field over this surface, then in this case, some of them are going to be, the ones that are coming out of the surface will be circulating clockwise, counterclockwise, so they are positive. The ones that are going into the surface will be circulating in the opposite direction. Some of them are going to be positive and some of them are going to be negative. And the general then expression for Gauss, for Ampere's law in this case, states that this integral is mu naught times the net value of this this magnetic field, of this current basically, with the assumption that the ones that are coming out in my picture in here are positive, the ones that are going in are negative. Okay? So that's basically what at the end of the day is. So this is an algebraic sum of the net currents. And the currents in here, you have to have them, some of them positive and some of them negative. I think the glitch probably for you guys may be this thing in here, which I'm going to include it in a little bit more detail into if you did polar coordinates, this also should be something that you have seen in math somewhere. Do you guys do polar coordinates at least in different, when you're doing the, you guys are taking Calc 2, aren't you, at least, or doing Calc 3 now? All of you, you must have. Okay. No, the ones who are, okay, good. So I think, do you guys do double integrals already? No, not double integrals. You don't need to do double integrals in, for this purpose. At least Calc 2, you should see the polar coordinates. Okay, good. So Calc 2. So this is polar coordinate. This is from math. So I'm going to include a little bit of stuff in here for this point in here because that seems to be probably the yes, polar coordinates and Calc 2. So I'm going to include, this is basically coming from polar coordinates, that's all. That is really the expression from polar coordinates. So I'm going to include something on Canvas for you guys to go through. I'm going to make it as probably as short as possible, no more than a single page, where you guys can see the this expression here. Once you see that, then it's a matter of just dot product in here, because B is going to be always in the theta hat direction. It cannot point to in the radial direction no matter what, because that's basically the right-hand rule. And now this dl, which is basically the expression with which you're going through the path, you could be going in the radial direction, you could be going in the azimuthal direction. So that could have two components, but it doesn't matter because you're going to do the dot product. The r hat times theta hat is going to be 0. So what is going to survive from the dot product of b times dl is this r d theta times b. And b has an r in the denominator. This is what we have seen. So the r and the r cancel. And once they do, then you're in business. Then you just integrate over d theta. Now you have two possibilities. Either you include the charge, which is like include the current, I'm sorry, like this situation, in which case you're going to start from an angle and go full cycle of 2 pi, come back to it, as you have completed the full circulation. Or in this situation, if the current is not enclosed in the path, then in this case you start from an angle, you go to some angle, doesn't matter what that angle is, and you come back to another to the same angle. So basically the integral now can be broken into two values, from theta 1 down to, I'm going to just do that part in here. So you're integrating from theta 1 back to theta 1, okay, of d theta. So you could say this is the sum of the integral from theta 1 to theta 2, some value, plus the integral from theta 2 to theta 1. And this is actually the negative of that. There is actually a theorem in Calc 1, I believe, this one, is where these two integrals are actually equal in magnitude but opposite in value. So this is 0. Okay? You guys remember that from Calc 1? Yes? Yes or no? I need somebody to confirm this thing. Because it's important for our Ampere's law. We have to have that understanding. Okay, very good. Okay, somebody confirmed it. That's very good. So basically, that is essential. That means that this current, and I think there is a homework problem already along this line, if you're counting them, they have to be enclosed. This is not different than when we did Gauss's law, actually. When we did Gauss's law, we were doing the integral over a closed surface, and the closed surface now better include those charges. If we didn't include those charges, the field lines, they come in and they leave. So whatever contribution is coming is cancelled by what they leave, and at the end, those they will have a net flux of 0. So the charges have to also be enclosed for that to work. Furthermore, also we had a 1 over 4 pi r squared in the electric field, and we have in here in the area of a sphere, which is 4 pi r squared. I mean, the r squared cancels the other r squared too. So this is exactly what is needed to cancel for the flux was the area which is proportional to the radius squared, whereas this one is inversely proportional to the distance squared. And here, in the case of magnetic field, my screen froze. Okay, good. Now it's responding. So in the case of the magnetic field, the magnetic field is inversely proportional to R, and the circulation is proportional to R. So the two are exactly what is needed to cancel. It's a matter of finding whether or not you're going around the current or not. Are you circulating around the current or not? So that's basically what that is. Okay. So this is Ampere's law. Now, when you're doing problems with Ampere's law, we have to observe the same rules, basically, that we did them when we did Gauss's law. So in Gauss's law, just to remind you, you better have some symmetry to do the problem, number one. Number two, based on the symmetry, you're going to choose a Gaussian surface, and that Gaussian surface, you may indent some of its properties that are not part of the problem. And once you indent a surface that is not part of the physical problem, any properties you add to it, they have to cancel at the end. They have to not matter. Otherwise, you will have a problem that is dependent on your choice of the Gaussian surface, and that doesn't make sense. So, and once you do that, you do everything using the argument of symmetry so that actually you don't do that integral. So basically, the whole point of writing it in this complicated looking form for law is that at the end of the day, you actually don't do the integral. You argue one way, you argue the other way, you move the electric field out of the integral, and just trying to find what that surface looks like, and then you find the enclosed charge, and that's it. That was one of the exam problems, by the way. where from exam, I don't remember, exam 2 or exam 3, where you were supposed to find this charge, and then charge enclosed, and you find it somewhere in between. So there was some geometry in there where the distribution of charge was involved, and you did some integration. Most of the work actually was involved with doing the integration for the charge, for the charge, not this side. Side in here was a little bit easier. Same thing in here. It's going to work the same. As a matter of fact, there are about 2 or 3 problems from the homework where you're going to be doing something similar. You will have a current distribution now given by J. So the vector J now is the current density, and the current density is over surface. So basically what you have in that homework problem, you have a wire that has a current running through it, and that current is not uniform. It's not all the way the same, whether you are in the center of the wire or away from the wire. So this changes with distance. So J is a function of R, okay? And of course, the current I itself is going to be the integral over this surface now of J times this area. The vector J, by the way, is a vector, okay? And it's in the radial direction. So in this case, what is it? Yeah, it's not changing with the angle. That's good. Otherwise, we will have problems and bumps and everywhere else in this case in here. So G times dA, and the area in this case is coming out of the, wait a minute. The J is in the radial direction. No, it's a vector, but it's actually coming, it's in the same direction as the current. Let's be clear on that. So it's in the same area as the, as this surface itself. So if the current is coming out, so it's in the n hat direction. So in the J times now the area dA, and A is actually in the same direction. So this dot product basically at the end of the day becomes that J times dA. Okay, this is from the homework, one of the homework problems, or at least 2 or 3 of the homework problems. They have current densities, and you're going to do something similar. The only trouble in here is going to be this side of the equation, trying to find the I enclosed. In here, you're going to make the symmetry argument, find the magnetic field inside the wire, find the magnetic field outside of the wire, find the magnetic field in the region between them, and basically you can find it. If it's a coaxial cables and you have currents running through some of them and you're trying to find the magnetic field, you can find the magnetic field too. So you can do a lot of these things, but mostly you have to observe the rules in here. So what are the rules? You have to choose what is called an Amperian loop. Amperian loop is similar to a Gaussian surface.
Sorry, is that an n hat up there?
Yeah, it's an n hat. It's in the direction of the current. This is a cut from the wire. So basically, this is this wire. If I come in here and cut it, and look at it from here, from this cross section. So this wire looks like this. So it's a big cylinder, if you wish. It's a very long cylinder. So if you come from this way, this is how you look at it. So this is n hat. And that is actually the direction of the surface A2. The current is supposedly flowing in this direction. That is the direction of J hat. That is the direction of the current itself, I. So if the current is flowing in this direction, I, this is actually the vector J hat. The vector J, I'm sorry. It's in the direction of n hat. N hat is the normal to the surface itself. N stands for normal in this case. Okay? So why did I put in here a vector on top of it? Okay, so J itself is a vector, which is in the n hat direction. Okay, so this is J. I wrote it in this way. So as J is a function of R, this is a homework problem, times n hat. N hat is in the same direction as the area, and the current now density is changing on the surface itself. So basically, it's probably far stronger in here, and as you move away, there is less and less current as you move around this thing. In uniform current distribution, J is the same everywhere on the cross-cut, on cross-section. In a non-uniform distribution, J may depend on this distance R, okay? And that is some of the homework problems, how they deal with the situation, and that's how we're going to solve it. In other words, similar to the exam problem, and the problem I remember when we were in face-to-face lecture, I think Sophia worked it out, or was it Aaron? One of you guys did, at least in the class. At least they did. I think probably there were 2. Now, Sophia worked probably the problem with the what is it, the electric potential. I think it's Aaron who's worked this problem, and it was for charge distribution. So the biggest problem there was finding the charge itself. So the biggest problem of the homework again is trying to find the current itself, enclosed. Once you find the current enclosed, then you're in business. You found this part, then in here you're going to use the symmetry. So we have to choose what is called the Gaussian surface, and the Gaussian surface follows the symmetry. And we're going to go back into the problem that we did last time and trying to basically do it with symmetry. So the first step is you have to find the symmetry of the problem. So this works only for a symmetrical problem. That's one thing. Choose an Amperian surface. I'm sorry, what is the Amperian surface? An Amperian path, okay? That's not a surface, okay? We're not doing surfaces anymore. So, and then whatever properties of this Amperian path it has, it cannot, they drop out. They cannot, the result should not depend on the properties of this. Result is independent of introduced properties. So if there are properties that you didn't introduce, they're part of the problem, the answer may depend on them. But if there are parameters that you introduced manually, they should not, the answer should not depend on those. So it is dependent of introduced properties of this Amperian path or Amperian loop. So you have to introduce an Amperian loop. This is not surface. This is a path integral. You're going to go around the loop to find the answer. Okay. So let's do a few examples, and I think the chapter will be done with it in a few minutes. Okay. So no, actually not a few minutes. There are some quite discussions. Any questions so far? Jackson, do you have any questions?
Nope.
Okay. I like your, now Aaron is on board. Or was Aaron here all along? I didn't see that. Okay, so we're going to take back our example that we did and basically trying to find the the magnetic field. And you see how simpler it is had we discovered Ampere's law first to try to find the magnetic field produced by a wire with a current I running through it. Okay? So in this case, I want to find the magnetic field in this point. Okay? And since that's the point of interest to me, oh man, my screen is not responding now anymore. I'm sorry, I have to stop it again for some reason. Sometimes it does that. Okay, now it's responding. I think this chat thing is on the way. Anyway, so I'm trying to find the magnetic field in this point, and basically we're going to use Ampere's law. So we want to find an Amperian loop in order to find the magnetic field anywhere on this thing. And we have to use symmetry in this case. And the symmetrical properties of this wire are the following. This is an infinite wire. So my argument is the following. If I move the wire one way or the other, it should not matter. That means this magnetic field should be symmetrical with respect to this translation. Basically, if you're not paying attention, if I have a wire that is an infinite wire, and if I tell you to close your eyes, and if I move the wire one way or the other, you would not be able to distinguish whatsoever what happened to the wire, because this is an infinite wire. You guys understand? So there is that's argument for symmetry. Furthermore, if I take the wire while you're not watching, and if I rotate it, spin it one way or the other, you would not also notice, because this is symmetrical. So it has this cylindrical symmetry. It's an infinite wire. So the magnetic field in this point in space is the same as this point in space is the same as this point in space. Because if I move, if you tell me, okay, it was 10 Tesla here and now it's 5 Tesla in here, if I move it, you will discover that somehow I have the point that was facing 10 Tesla now is facing the 5 Tesla, and this point should now read 10 Tesla, because where is that effect is coming from? It's probably from somewhere in here. There is more current in here than in there. So if the wire is infinite and uniform, you shouldn't see any changes in the magnetic field. If you were reading 10 Tesla in here, you should read 10 Tesla in there. So the same number as far as the magnetic field. So there is that symmetry. So the magnetic field is the same everywhere, anywhere a distance r from it. That's one point. The second point is, if I spin it one way or the other, it's the same value. Now, there is another critical point in here. If you somehow argue that the magnetic field is pointing one way or the other, then all I have to do is, while you had your eyes closed, rotate this whole wire, okay? Obviously, in this case, the direction of the magnetic field, the current will probably flow in the opposite direction, and the sign should matter only not in this direction. So if you were arguing one way or the other, again, we're going to cancel it by that argument of the symmetry, or spin it, and the direction should not cancel. At the end of the day, these are the only two directions that should conserve symmetry. Again, I'm coming to here and look at this wire while looking at it in that direction. So this is how the wire looks to me. So there is a wire and it's a current running in, and I'm trying to find the magnetic field in this point. By symmetry, either the magnetic field pointing this way or pointing that way. The first one is not going to work for me because I'm trying to find the circulation of the magnetic field and argue that that is equal to mu naught times this I. So this I know, okay? That's part of the thing that I've given. This distance is r, okay? Now, having said that, then, the only direction that is acceptable is parallel to dl. And furthermore, the magnetic field should be the same everywhere in here at distance r from it, because if I spin it one way or the other, it's going to remain the value the same because of that symmetry. So this value is the same as long as I am on this circle. So the Imperial loop in this case is going to be a circle of radius r, okay? So my choice of the Imperial loop, this is the Imperial loop to which I'm going to do the calculation, this calculation. So B is constant both in direction, it's in the same theta, it never changes as long as I am on the same theta, number one, in direction, and in value also it's independent of R. Basically, I'm sorry, it only depends on R. Since R is not changing on that loop, B should come out of this integral. So this whole integral, first of all, the dot product becomes just a normal product because dl and B are in the same direction. And basically at the end, this mu naught I times the integral, B comes out of the integral of dl. And the integral of dl is no more than just how much is the circumference of a circle. Because that's basically what my Imperial look like. So this is 2 pi r, that's the circumference of a circle. And from here, I find that the magnetic field is equal to 1 over 2 pi r times mu naught I. This is exactly the same thing that we did the other day with the integral. I mean, we had to do the integral, we had to do cosine here, a sine of theta here, and a cosine of theta there, and integrate from theta naught to negative theta naught, take this angle to go to infinity, basically. So I'm integrating from negative pi over 2 to positive over pi over 2, and at the end of the day, we found this result, okay? So it was a long way of doing it, but this one also is the same thing. But you have to do dense in here, and this dense is the following. You have to use your symmetry argument to, first of all, make the case for the dot product, and second of all, to pull the B out of the integral, and basically do a trivial integral, which is in this case just a simple circumference of a circle, which this is basic stuff. You don't even need calc for this stuff to understand that the circumference of a circle is 2 pi r. Now, the properties of the Imperial loop do not exist in my answer because R is actually a fundamental property of the problem. We're trying to find the magnetic field at some point somewhere, okay, near the magnetic field. Okay, so this is one example. The second example we're going to do is going to be the solenoid. And the solenoid is a big deal. Solenoid. I know it's a big topic nowadays, the paper, the toilet paper. So if you're done with the toilet paper, you serve the thing inside of it. Okay. This is how it looks like. Okay. After the paper is out, or kitchen towels, basically, this is the shape that you'll be left with. Basically, that cotton-based thing in here that you have in there. Okay, don't throw that. So go and grab a wire from Home Depot, and run that wire in the following fashion. I'm going to bring the wire, and I'm going to turn it around this structure, and I tightly connect it. So I mean, it looks loose in here. I shouldn't do that. I should basically make as many as I can in here and then run the wire in here. Do you guys see this picture? Do you guys understand how this works? Okay, very good. So basically, wrap a wire around any cylindrical structure and tightly wrap it in here. Basically, how many wrappings you're going to do, how many times it's going to go around, I'm going to assume that you're going to have an N number per meter. So the number in here is N per L. So basically, you're going to have, let's say, for example, you wrap it 100 times over 10 centimeters. So in this case, you have 100 turns per 10 centimeter. So N in here is the number of turns per unit length. Okay. Now you connect this whole thing to a battery and let the current flow. I don't like this. I'm gonna do flow it this way. Okay. But I want the current to come again clockwise, so that the magnetic field at the end of each one of them is going to come this way. Okay. So this will be the North Pole, and this will be the South Pole. You guys understand? So basically, at the end of the day, this is the structure I'm looking for. I'm following the right-hand rule. I mean, if we do it the other way, it's going to work, but the magnetic field, the north and the south, will flip. You guys see the argument in here? I had to put the positive end of the battery on this side so that the current will go around several times and merges from the other end this way. So there is a current I now running through this loop. Okay. What I'm going to do now, I'm going to do a mathematical cut, basically, not a physical cut. If you cut it physically, this is not going to work. So what you do in here, you come with the mathematical scissors, and you cut this from top to bottom, basically, and this is how it looks like. So basically, it's a half now structure. This is how it looks like. And this is, so now there is a wire going from this end, but only half of the wire. So the current is going in now, and it's coming out from the other end. And it's going in, and it's coming out, and so on and so forth. So it's still going counterclockwise, basically. So there's a bunch of them. I put them spaced. I don't mean them to be spaced, honestly. They need to be really closely packed in order for me to strengthen the magnetic field. Okay? And there is an N number of them per unit length. So there is N turns per unit length. And these wires are going into the surface and going into the surface and coming from the other end and so on and so forth. This, if you really cut it, it's not going to work because the current cannot go anywhere. You guys see that? You understand that this is just a mathematical basically representation of this thing. Okay. So now let me actually do it in a different fashion in here so that we see it. So this is how it looks like actually when you look at it straight up. So I have a bunch of wires going in on one end, and I have a bunch of wires with currents running through them. I know that at the end they will connect. It's actually the same wire wrapped several times. But for me, through this cut, it looks like I have a bunch of currents going in and a bunch of currents coming from the other side. So at least the surface that we're looking at. And we want to use Ampere's law to find the magnetic field here, outside, and here, inside. Here, it should be the same value of what we find from the other side. So the first step is to find an imperial loop, basically, to find the magnetic field outside. I'm going to take an imperial loop in here. Let me remove this here because it's in the way, actually. So I'm going to draw an imperial loop. Imperial loop is going to be a simpler imperial loop. In this case, it's going to be actually a rectangle. So it's going to be a rectangle of length L and width W. Okay. Are L and W part of the problem, or did I just invent them? Need some help here. You guys need to tell me. Are L and W the properties? So they are invented according to Jackson. Anybody
Are you
else?
talking about like the circumference and then the length of the roll?
Now, this is basically, I'm trying to use Ampere's law to find the magnetic field outside of the of this structure. Remember, the actual structure looks like this. Let me get this in. This is how it looks like, okay? So I'm trying to find the magnetic field in here and in here, outside of it. There's a current now running through this one, this wire. And that current is going to create a magnetic field. This is an infinite loop, infinite solenoid, by the way. This is very long. I know I cannot draw it this way, but this is supposed to be an infinite solenoid, okay? Otherwise, we'll have a problem with the edge effect. So this better be infinite so that we don't have to worry about what's going on at the edges, okay? And the question is, I need to use Ampere's law of the magnetic field outside. Okay, so the first task is to find it outside. Then we'll find it inside. Once we're done with this too, then we're in good shape. Okay. So outside, far away from it, far away from the solenoid. What I'm saying in here, this is an Amperian loop. I'm choosing of shape, as I'm going to choose as a rectangle of length L and length W. Jackson seems to think that this L and W are something that are just made up, basically as part of the imperial loop. Do you guys agree or not? Or Jackson again? Okay, Gareth also agrees, Winter agrees, so good. So we have a little bit of consensus. Yes, this L and W are not part of the problem. What is part of the problem is probably the radius of this structure, so R maybe, okay? What is also part of the problem is that N. What is also part of the problem, so N, which is the number of loops. What is part of the problem is I. What is part of the problem also is probably the medium where we're putting this. So expect the answer maybe to depend on N, how tight I'm going to wrap this turn, number one. It's going to also may depend on the current. If I don't have any current, I should not see any magnetic field anyway. It may depend also on the medium that I have in there, its properties, and it may also depend on smaller or bigger. So that's basically the answer to that question. You guys understand? So this L and W have no business to being part of the answer at the end of the day. Having said that, then I'm going to use the Ampere's law, trying to find the magnetic field in this region in here. So let's assume that there is a B in here. And again, I'm going to use the argument of symmetry, and he argued that the magnetic field should not be, again, because each wire is doing like this. Let's take this wire in here. It has the current going into the surface. So the magnetic field produced by this wire and the combination of these wires needs to be perpendicular to these wires, and this is the direction with which it's going to be perpendicular, or this direction, of course. It could be positive or negative. It could be pointed, but it has to be down now since I'm in this region. So this class 2 should not really be correct. So because the current is going in, so the magnetic field, if it exists, is going to be pointing down. Therefore, the contribution of, when I'm doing the BDL, on this part and on this part, the B should be either down in this case, and the DL should be down, but in here, the B is down and the DL is in this direction. So the contribution in here is 0, and the contribution in here is 0. That is because of the dot product. It has nothing to do with anything else. So this integral for this Ampere that I need to do can be broken down into 4 integrals. I'm going to call this one contribution 1, contribution 2, contribution 3. This is the closer part to the from the Imperial loop to the solenoid, and this is contribution 4. Okay. You guys see that this part through path 1 plus the integral through path 2 plus the integral through path 3 plus the integral through path 4, they must be equal to, in this case, the whole thing, first of all, these 2 are going to be 0. Okay? And now, in this case, how much current I have enclosed in this path? In this Imperial path, how much current do I have? How many currents are going in or out of the surface here? Do you see any? Is there any wires?
The number of n times I. Okay. Yeah.
How many wires? I mean, in this path in here, which is a rectangle of width W and length L. Do you see? There is no current. Do you guys see that? There is absolutely 0 current. So from one side, it's mu naught times 0. Okay. From the other side, again, you guys see that the contribution from number 2 and number 4 are 0 because DL is this way, and the magnetic field, by argument of symmetry, needs to be pointing down if it exists at all. Therefore, there is no contribution from paths 2. I'm sorry, paths 2 and 4, not paths 2 and 3. Paths 2 and 4. These are the ones that are 0. Paths 1 and 3 are not 0. Okay, paths 1 and 3, there must be some value in here. And let's see what that is. If the magnetic field is pointing down in this case, let's say, for example, let's say there is 2 Teslas in here, doesn't matter. Tesla, this line integral is, again, because this is an infinite solenoid, if you tell me it's 10 Tesla here, it's 10 Tesla in the bottom too, because if it's different, they can move it up and down and change the value. Since this is an infinite solenoid, again, the value in here should not be dependent on W. If it's the value here, it's the same value here, same value everywhere in here. So when I'm evaluating the integral on path 1, the value should be the same value for B, so it is going to come out of the integral. So, and because B in path 1 is pointing down, and I'm integrating going up, I'm still going it clockwise on that path integral. So this integral is actually going to be negative B on that side. So negative B on the region 1, which I'm going to call it B1 times W, plus 0 from region 2, because they are perpendicular, plus now B and W in the same direction. B is going down and W is going down, so the dot product is going to be positive, but B on region 2 is actually, region 3, I'm sorry, is probably different value. So I'm going to call it B on region 3 times W. This must be equal to 0 because there are no currents enclosed. And what is the obvious conclusion to this one? How much is B1 and B3 in terms of one another? It should be W from both sides, because again, the answer should not depend on the W. So this indicates that how much is the value of B1 and B3 are?
0.
Are they 0 or are they equal?
The same value here.
They are the same value. Do you guys see that? That B1 and B3 are the same value. That means that if I am closer to the solenoid or far away from the solenoid, it's the same magnetic field. So B out is the same value here. Sorry. So if I took a device in here and measure the strength of the magnetic field and find it to be 10 Tesla, 10 Tesla is through the same everywhere outside of the solenoid. Because L, I can stretch it as long as I want. The answer doesn't depend on L. You guys understand that? Now, a particular point that I think I know what the magnetic field is at infinity. How much do you think the magnetic field should be at infinity, far away from the solenoid? How much should the effect of the solenoid be on the other part of the universe? Would it have any effect at all?
The same.
How much? We need the value in here. We need to, based on physics now. We need the number. Far away from it. Did you say something? Okay, somebody here is. So somebody saying 0 effect. And the reason for it is very simple, because when you are very far away from it, there should be no magnetic field. Is that what you said, Aaron? Probably I misunderstood you. Did you say 0 too?
Huh?
Did you say 0 too when you intervened earlier?
Not what I said.
Okay. It should be 0. So I can see far away from, I'm sorry, I should have really not done that. Okay, great. So far away from the solenoid, the magnetic field should be 0. I mean, when we are far away from it, there should be no effect whatsoever of the solenoid, whether there is 1 amp running through it or 10 amps running through it. Far away from it, there should be no magnetic field. And the magnetic field is the same everywhere outside of the solenoid. Therefore, I conclude that the magnetic field is 0 everywhere outside of an infinite solenoid. So B at infinity must be 0. Since B is the same everywhere, this is the argument that we use now for based on Ampere's law. Therefore, B on an infinite solenoid outside should be 0 everywhere, not just at infinity. That's the only value that makes sense, so that this integral is true no matter how stretched or compressed L is. Since this choice in here for the Imperial loop is our choice, we can put whatever L is to be. And since we can argue that this integral in here, which is a negative value, is the same as this integral, which is a positive value, therefore in this case, hey, the two values must match, and the only thing, since this side is 0, therefore this one also is 0, and the magnetic field everywhere here is 0. The same thing is true is here on the other side too. The same argument holds on the other side. So the only thing of interest is the B inside, basically. How much is the magnetic field inside the solenoid? And that is what the purpose of the solenoid is, create magnetic fields. And the purpose of them, to use them in devices, actually is to concentrate the magnetic field in a region. Okay? So just like capacitors in the old days, where you use them to hold the electric fields, you will see that this is useful trying to trap the magnetic field. So I'm going to draw again the shape. I have current running in. And I want to find B inside, how much it is. Again, I can use the Imperial loop in here, inside, and argue that B here, and B here are the same value. Because again, I'm not enclosing any currents in here. B must be perpendicular to the path in this side. So that product contribution is 0. B is perpendicular to this path, and that must be 0. The B on this side and the B on this side is the same. For an infinite loop, the magnetic field is the same anywhere inside the solenoid. So it's a matter of finding it now. Do you guys understand that the same argument I used outside to argue that the magnetic field is the same everywhere can be used also anywhere inside the solenoid? the magnetic field is anywhere, which gives me this thing in here, which may indicate that the answer may not depend on R. Because if it does depend on R, then there may be an imbalance in terms of this value. Okay, if R is a fact, then so the answer may not depend on R because of this argument. And let's check it. Okay, so I'm going to take this Amperian loop now, and I know how much magnetic field is in here. It's 0 actually. And let's say there is a value here which is B inside. If there is a magnetic field in here, it's going to be perpendicular to this path. Again, this is W, this is L, and this is W going in. So in this case, I'm going in the negative direction. You guys see that I'm going in the negative direction? If I'm going to go clockwise in my integral, then this product contribution from area 3 is going to be 0. So 1 is 0 because B is 0. 2 is 0 because actually B inside is perpendicular to L. Okay? Outside it's 0. In here it's 0, so there is no contribution. And in here, in this inside portion of it, actually it's not 0 because B is 0, but it's 0 because B and L are actually perpendicular to one another. So this whole path integral boils down to finding this negative number, that's all. Okay? And this negative number is B is uniform and the same again, because if you tell me B on the top here is different than B in the bottom, all I have to do is move the solenoid up and down, and then, hey, I discovered that there is a problem in here. So there is this symmetry in here because it's an infinite solenoid. Therefore, B is actually the same value everywhere in here, and it's the same value no matter how far you go up and down. Now, having made that argument, then this integral on the other side will just be equal to minus B times W. So from one side, it's minus B times W. And now we have that problem with W. We have to get rid of it because it should not be part of the answer. On the other part, it's going to be mu naught times the current enclosed. Now, how much current do I have enclosed? First of all, the current is going into the surface in here. And this current going into the surface is a negative current. So there is a negative sign in here. Okay? And having said that, then let's see here what we have in here. Okay, I'm trying to make sure. Okay. Having said that, then this is basically the end of the current. How many wires do I have enclosed in a W? Remember, I have N wires per unit length. This is N, I'm sorry, not N wires. It's N number of turns, but it's N wires actually per meter. But I don't have a meter in here. I have a W of it. So how many actually I have?
N times W.
NW, do you guys see that? So I have N times W times each one of them is carrying a current I.
Current.
That's how many currents I have, how much current I have enclosed in this Amperian loop. Oh, that's nice, because then the W and the W cancel. That is critical piece of a step in the calculation in here, because this W and L have needs to be part of the answer whatsoever. They're just made up numbers, and at the end, the answer, as suspected, for the magnetic field is going to be equal to mu naught N, which is the number of turns per unit length, times I.
Times current.
Yes. This is so basic, important stuff. I know when we started, we said that you guys need to go and do hands-on and stuff like that. If we're going to build a solenoid at your home for probably your motorcycle or something like that, or something, I don't know if it needs this kind of big of solenoid or something. There is a place actually in San Bernardino that rebuilds what you call them, those alternators and things like that, and they have a lot of wires, and that's what they do. They have a machine that actually makes those wrappings in there. Okay, so that's a useful piece of information. That's how much magnetic field you have. It depends on, of course, the properties of the medium. So and that is something that is actually useful also if you're going to be oh man, I lost the okay. for example, when you come to a red stoplight in a red light, the way that we're going to talk about that later on, but basically the material that is in there you will disrupt its current in there, and when you do that, you'll induce a current. So we'll leave that to the next chapter, actually, when we talk about Faraday's law. But the point in here, you can build your solenoid, and this is how much magnetic field it creates in it. And it's the same thing everywhere. It doesn't depend on R. We suspected it might not because of this fact in here, and it did not. Okay? And it depends, of course, on the current. If there is no current, there is no magnetic field. It depends how densely packed your turns are, how many turns you have in that. And it depends, of course, on the properties of the medium in there. If you were to change it to a different material that has different permeability properties. Okay? So, this is an infinite loop. We're going to close today's lecture with another. This is the last part of the chapter. So we're going to introduce it, and then we're going to talk about homework problems. And that is this kind of solenoid. This is probably more practical than the first one. Actually, both of them are useful. I'm sorry. I should have not said that. So basically, it's a donut shape. You take a wire and you bring it again, and you wrap it in here around this wire. So I'm trying to draw it in here. Okay. I think I put it backwards. Anyway, so basically that's how it looks like. And you send the current. I'm going to make a cut again. This is a mathematical cut, not a real cut. So again, this is a donut. So this is a, what is this called again? It's a toroid, or what is it called? I'm sorry. I'm looking at your book in here. See the name for this thing in here.
Toroid?
Yeah, toroid. I don't know. I'm sorry. I know it in French. So, yeah. So this is how it's called, okay? So, it's a donut shape, basically. Don't grab a donut. Don't eat it and wrap the wire around it, okay? So that's basically how you can do it. So, I'm going to make a mathematical cut, and again, this is how it looks like. To me, let me see if I can, it doesn't matter which way we're going to do it, basically. So again, it has an inner radius R and an outer radius R1. So this is radius A, and this radius is B, okay? And somewhere along, there is an R in here. I should have drawn it a little bit bigger to see the differences in here. Let me draw this thing in here, since there is a free space in here. Unlike the classroom where we were limited by the number of bolts and every time we have to erase. So there is an inner radius and an outer radius in here. So this is your inner radius, this is your outer radius. So where is the distance R from somewhere? I'm trying to find the magnetic field at that point. At some point, we have wires that are coming out with a current that is coming out. So in here, I have a current that is coming out. But now I have a finite number of them. This is not infinite. I mean, no matter what, I'm going to have a certain number of this wire. Of course, because of the geometry, the outer ones will be a little bit spaced because it's the same number of wires. Okay, so they are not. It's not like you have more wires outside than inside. So once you wrap like 10 wires, the 10 will go in and the 10 will come out. Okay. So at the end of the day, when you make the mathematical cut, this is how it looks like more or less. Okay. And I want to find the magnetic field first of all outside, B out. And I'm going to find B in. No matter which surface I choose, no, I'm sorry, not surface, which loop I choose, if I am out, I'm going to choose a circle of radius R that is equal to the radius of outside region. And no matter what I do in this case, there is a number of wires that are coming out is equal to the number of wires that are going in. So from here, I immediately conclude how much is B out is going to be. If the number of the incoming is the same number of the outgoing, so the net value on the outside from, if I use Ampere's law, is going to be
0.
0, because Ampere's law requires that I sum all of the current algebraically of the incoming plus the outgoing. That should give me 0 on this side. Because once I wrap a certain number of wires, they must come from the. So B out is going to be 0. And so is B inside also, because there is no wires inside. So this B in and B, both of them must be 0. And the reason is because either I'm enclosing an exact number of currents that are going in and the same number that are coming out, or I'm enclosing nothing here. One of the two is going to give me, both of them are going to be equal to the same one another, and they're equal to 0. So this device is actually useful because it traps actually the magnetic field, and I don't have to worry about that infinite link, because if I don't have an infinite solenoid, the problem is going to be in the edges. The magnetic field is not going to be uniform and stuff depends on R, and there is the edge effect. In this one, I don't have to worry about that. So this is actually a far more useful one. And if you open any electronic device, you'll find a bunch of them actually, especially near the power supply where they regulate currents and things like that. So this is actually a common device in most of the electronics that you see. Okay. Okay. Open your computer or TV or OTV, that is, not the plasma TV or anything like that. You'll see a lot of them in the circuitry. Anyway, so let's try now to find it somewhere in this region. So again, I'm going to choose an Imperial loop that is actually a circle in this case, and of radius r. I'm going to find the magnetic field in that region. Again, because of this symmetry, if I rotate it one way or the other, the magnetic field should be actually also retain that circular symmetry. And circular symmetry now can be observed by the radial direction. If I were to, I'm sorry, not the radial direction, the azimuthal direction, if I were to find the circulation that is non-zero. And the circulation is non-zero because of the fact that they have currents that are coming out. So the magnetic field is actually in that direction, as I pointed. So this is B of theta, okay? And there is only one B. There will be no B sub R. So B is in the theta direction. It may depend on R, but it's not in the R direction. It's not in the R hat direction, to be more specific. So it's going to be in the theta hat direction. So having said that, then, and B should be the same because, again, if you tell me that it's 10 Tesla in here and 5 Tesla in there, all I have to do is rotate it, and since there is that symmetry, so you should discover that I have rotated it. So if you can't, then the same magnetic field is the same everywhere in here, okay? So that's argument for the symmetry. So B now is going to come out of the integral, and all is left in here for my value here is basically, I have B times the integral of dl over a circle and that is 2 pi times this r. Yeah, okay? And on the other side, it's going to be mu naught times the number of currents coming out. How many currents coming out in here depends on how many times you wrap it. And this is a given number. So this is n, and I is the same current running through all of these wires. Remember, all of these wires is just a big wire that is wrapping itself several times. So how many terms you make it? At the end, you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, or a million, or whatever, 100 of them, or 20, 300, whatever number you have in there. So it's a given number times mu naught times I. So that gives you magnetic field then in that region, which is in the azimuthal direction, but strangely enough, it depends on R now. So unlike in the first case in there, so B is going to be equal to mu naught times n over 2 pi r. I'm going to write it this way, times I. Why I'm going to write it this way? Because if I take r to be infinite, if I take this wire in here and make this little a to be infinite, and this b to be infinite, now I'm back into a solenoid that has a radius that is infinite. And if r goes to infinity, n also goes to infinity, because I need to maintain that ratio basically of wrapping. And all I'm going to do is find the ratio with which I'm wrapping, because now the solenoid will be basically, it's like you open it and it's going to be a big of length 2 pi r. That's the circumference of the circle. And in this case, n is going to just define the properties of this very, very long toroid. So I'm back to the solenoid now. And the answer is going to be, again, mu naught and I. Remember how I always ask that things need to be connected and see whether or not it makes sense or not? This is one way of looking at it. If I were to take the solid and make it into a huge radius, I am back into the situation that I just made the argument for, namely of an infinite solenoid. So, and the answer should match. The answer is actually the same thing as before. This is what we found for the solenoid. And in that limit, when n becomes a huge number, because they have to include to maintain the same properties, the physical properties, they have to increase n with r, maintaining the ratio to be constant. And this is the ratio, which is the density with which I'm doing the turning, basically. There are how many times I'm wrapping that wire along it. So again, I'm going to get the same magnetic field, and now the magnetic field doesn't on R, as we have found it earlier, basically, for the infinite solenoid. So this is basically Ampere's law. It's useful usually in doing these calculations. Later on, we're going to take some of these results from chapter 29 and basically try to use them in for our basically inductors and things like that. How do you guys find the magnetic field compared to the electric field? Because we're done with this chapter. Anyone?
Similar.
There's a lot more to the electric field.
Yeah, actually, it's very involved. You're right, and you really have to think about it. For this part of the electromagnetic field, honestly, when you're doing Ampere's law, it's a little bit easier than doing the electric field. But that's really a small part of the problem. The biggest problem overall is that the magnetic field is a little bit more math involved, more stuff involved than the electric field, and that's really how this usually goes. Let me quickly take the attendance. So I'm going to stop sharing the screen. And for some reason, we have two people who are not here, and the two people are Gino and
Oh yeah, I showed up 12 minutes late. Was there anything about like a lab or anything?
Wait, hold on. Let me first of all do a print screen quickly here, if you don't mind. Yeah, we talked about a lot of things when you came. Did you hear us talk about the exam also?
No.
Yeah, basically the exam is going to be a take-home exam. We're finished now with chapter 28. Chapter 28 actually, some of its content is actually on YouTube, and you guys are. I know we did a little bit of review of the stuff that was in YouTube before, and even the stuff that we did together last time around. And I want you guys to do that. Read the chapter, do the examples. I know probably I didn't do a lot of examples. Maybe we should do one or two before we close the session if we have some time. And what else? So that's basically for the exam. For the exam 3 that we took just before everybody else told us to go home and don't come back. I did not grade it yet, so I'm hoping to have it graded this weekend so that you will have your grades for it. And if you did I post a solution for exam 3 or not?
Yeah.
Okay. So yeah, so you guys have you will have a grade before actually taking exam 4. You will know exactly where you stand in terms of your overall grade for this class. And also the lab, there will be lab next week because we should do things this Thursday. Today's lesson is not going to be happening because I don't see it's a good idea to start chapter 29 today because we're just still fresh with chapter 28, and chapter 28 did not sink in yet. And you have homework problems for chapter 28. And if you have any questions, please ask them. They don't have to be necessarily during the live session. You can still be working on the problem, and if it's not clear or something, or need some working out or something, please do ask them. So I'm hoping that you guys start working on the homework problems for this one. Don't forget that you have a homework that is due this Thursday, and you'll have a new one which is due next Thursday, and you'll have actually chapter 29, which most likely will be due also next Thursday. And chapter 29 has a little bit of I want to say a little bit easier, but probably we will see. Okay, it's similar to the capacitance we'll be doing with the inductance, except that the capacitance was building up charges. This one was building up currents in the circuits. And once we have that, we should be able to do a circuit. If we can finish it by Thursday, I'll post it for you guys on YouTube. So you can actually do this stuff, namely for the lab, because we will have to have a lab next week. Somebody asked, again, a lab is going to be simulated lab. Basically, where you have the three different possibilities for circuits. You will have an RC circuit, you will have an RL circuit, and you will have also an LC circuit, an oscillator circuit. We may have to do without the oscillator circuit, we'll see, okay? And each time you're trying to find the time characteristic, and the first one is just 1 over RC. RC is the time characteristic. The other one has to do with the ratio of L and C, and another one also with the L and R. So basically, each time we're dealing with the time characteristic, and that's the whole purpose of the lab. So you're going to run the simulation, find the different values, and once you do that, you're going to submit the lab report. So you're going to start the lab activity on next Tuesday, and we will go together into how that simulation works. You're going to go and collect your data, and then submit your lab report later on. Okay? So that's everything in terms of this class. Is there any other question related to what we're doing? Because I don't know. Right now, I think.
About the test, when are you going to give it to us, and like how long do we have to complete it?
Okay, the test is not going to be, it's going to be a take-home test. It's most likely it's going to still the same format because although we did 3 chapters only in this part, like just most of the parts, it's going to have 4 problems. And the 4 problems, basically, you're going to solve them. It's an open book test, so they're going to be a little bit of a challenge compared to the previous tests, because the previous tests, you didn't have access to resources like this one you do. After the exam, you have to be ready to be contacted by me to go on a one-to-one session on Canvas. No, not on Canvas, I'm sorry, on Zoom. I may ask you 1 or 2 questions on that one to make sure that you know what you did on that exam, so that to make sure that your work cannot communicate with one another. You cannot work together on those problems. Okay. The time limit, it depends. Honestly, I didn't decide on that. It's not going to be a week. It's not going to be 2 days. It's going to be a lot shorter than that. So you probably have to work out very quickly, check your resources, and submit the answer quickly to Canvas, and take pictures of it, email them to me if somehow the Canvas is not working for you or something like that. Okay.
Okay. And when is the one-on-one meeting gonna take? When will the one-on-one meeting take place?
It's going to be after the exam. After you guys submit the exam, and I go through each and every one of them, then I will contact each and every one of them separately, and we'll have to go through basically in that case, I need you to share your camera if you have access to it, and explain to me basically your work. Okay?
Okay.
Okay. Any other questions? Again, today there is no class, so there was a class, and this one lasted for a long time. I don't know how this one is right now. It's almost more than 2 hours. And it's doing lectures for that long and doing demos and stuff like this one. It's kind of long sometimes. So I'd like to do a few demos. You guys are ready for it, or should we call it a day? Depends on you guys. I know it's been a lot. Or do you want to have it consumed a little bit, and later on we will do the examples?
I'd be fine with doing an example later.
Okay.
Answer.
Okay, guys. Then you have a good rest of the day, and I will see you guys on Tuesday. On Thursday. And you have the links on Canvas. Please go to YouTube, because I'm going to be posting stuff. Most likely, I will be posting this thing. I will not be posting anything else for a class other than probably depends to see how I'm doing with the other classes. Okay? Have a good rest of the day, everybody.
Okay.
Okay, bye.